Hi guys, welcome to video 6 where we'll be looking at the pedigree diagrams that you faced in tutorial 9. Okay, so for the most part this doesn't matter what kind of line diagram or arrow diagram that they give you, the steps are really straightforward so long as you stick to these ones, which I'm going to show you in the video. At the end I'll write them down in point form so that you can see exactly how it goes, but I'm sure most of you will pick it up as we go. So the first question gives us this diagram where we have offspring X, which has parents S and D. S has parents 1 and 2, and D has parents S and 3. And we've already described this, but S has parents 1 and 2. Sorry, there was another mosquito. I almost folded them. Okay, so the first thing that we have to do in this question is it asks us to draw an arrow diagram for the pedigree. So the first thing we want to do is start with the latest individual, the youngest individual, which in this case is X. X has parents S and D, and we can draw a line from parent to offspring. S has parents 1 and 2, so we can draw arrows to S. D has parents S and 3, and it gives us no information about individuals 1, 2, and 3 in terms of their parents, so we ignore them for now. So that is our arrow diagram. If you want to condense it, and this is usually a good idea for the exam, you can do two things, or one thing to start off with. You eliminate all the individuals that only have one arrow coming away from them. So if it has an arrow going to it, leave it, but if it has an arrow going away from it, like numbers 1, 2, and 3, but nothing coming to it, you can eliminate them. So in the exam, I would suggest doing the big diagram in pencil, getting rid of those extras, and then redoing it in pen. I would do it in pencil now, except the pencil doesn't show up on the camera. So I'm not going to do it in pencil now. You just have to deal with my scribbles. The next part of the question asks us to estimate the inbreeding coefficient of individual X. Now most of us know that our inbreeding coefficient is F, and F can be calculated as a half to the power of n, where n is equal to, now there's two ways to do this according to Oliver's notes, but the one that I like to use because it's the least confusing, it's the number of individuals in the pedigree, the number of individuals, excluding the individual of interest, or so excluding X, which is our individual of interest. Okay, so in this pedigree, our F value would be equal to the number of individuals in this pedigree, 1, 2, 3, excluding X. Okay, we can't use X, so it's 1, 2. So our n value is 2, and we should get 0.25 as our final answer. Very simple. What does this result mean? It means that this individual is 25%, it means that there is a 25% decrease in heterozygosity of that individual as compared to other individuals in the population who weren't unbred, or that were not inbred. Okay, so that's something you need to remember from the notes. I'm not going to write it down. Right, for the second question, there was a slightly more complicated pedigree. So let me draw it for you. It was individual X has parents S and parents D. S has parents 1 and 4. D has parents 1 and 5. 1 has parents 2 and 3. 4 has parents 1 and 6. We know about 1. We already said that he has parents 2 and 3, and 5 has parents 7 and 8. So now we're going to do the exact same thing that we did with the first pedigree, where we're going to try and condense it as much as possible by starting at the bottom. So we have individual X. X has parents S and D. Alright? Individual S has parents 1 and 4. Okay, D has parents 1 and 5. Okay, individual 4 has parents 1 and 6. And then individual 5 has parents 7 and 8. Okay, so this diagram will look pretty confusing. Depending how you draw it, sometimes you won't have lines that cross. But in this case, I do have lines that cross. And that's okay. Don't worry about it yet. So the next thing we're going to do is the same as we did over here, where we get rid of the individuals that only have one line coming away from them and nothing coming to them. So that in this case would be individual 6, 7, and 8. Now we do the same thing again. The point of this is to keep doing it until you have closed circles. Now if you look here, 5 in this situation has the same story. He now has nothing contributing to him, and he only contributes to one individual. So we're going to cut him out as well. Now we are left with closed circles. When I mean closed circles, you can run a line all the way to the top and it can go down back to the bottom again. Or it doesn't matter how many paths there are, but you can do that. Then the next situation here is to isolate the inbreeding events which are happening. In this situation there are 2. How do I know there are 2? Well, in order to establish that there is in fact inbreeding, and I will use this first diagram as an example, is to start with the bottom individual, draw all the way up to the most recent common ancestor, okay, and then when it doesn't go up anymore, we draw all the way back down to our individual X along these arrows. And if it makes a closed circle, then we know that there is an inbreeding event. So if we do that with this diagram, we see this. Okay, let's start with X. X can go up. Actually, yeah, okay. X can go up to D, can go to 1, and then it can come back down to X again. There's one inbreeding event. Okay, for S, if you look here, it also has 2 arrows coming down to it, alright? Which means it's also the point of some line. So if we start that there, we can go up to 4, around to 1, and then go back down to S. So there's a second inbreeding event there. Now I know that looks very untidy, but if you draw it yourself, you'll see exactly what I mean. So question B, after we've drawn this pedigree, obviously we don't want to draw circles on it as part of our answer because then it'll make it look messy, but you can in pencil, is we want to calculate the inbreeding coefficient of S. Now we've already identified the inbreeding event for S, which we said in that closed circle is S comes from 4, who comes from 1, who also contributes to S, and there's our closed circle. So therefore, in order to calculate our inbreeding coefficient for S, we use the same formula as before, where N is the number of individuals excluding our individual of interest, which is S. So it's 1, 2, which is 0.25. Then it asks us to find the inbreeding coefficient of x. Now x, if we redraw that inbreeding event, we'll have from 1 to d to x to s, which comes down. Then, because we chose 1 in this situation, we're going to go back to 1. Don't worry about the fact that 1 also goes to 4. That's a separate event which we accounted for over there. Okay, so now you can see our separated inbreeding events by our closed circles. So now to calculate our inbreeding coefficient of x, we do the same thing. Half n, which is 1, 2, 3. However, in this next part, we already know that individual s was already inbred. So we have to account for that. So what we do is we times whatever we have here by the 1 plus the inbreeding coefficient that we previously calculated for fs. So we're going to have 0.2125 times 1.25. Remember, it's 1 plus. Should be 0.156. Okay. Now, we've forgotten something, and this is very important because this is the formula that we would use for Oliver's section. That's in his notes. But this value here is only applicable when your S, or your most recent common ancestor, is at the top of your pedigree. Now in this case it's not. It's one level down. So we take away one n value and recalculate it. So I'm running out of space here, so I'm just going to do it like this. I really hope you can see. Is now instead we're going to have half to the power of 2, which is 0.25 times 1.25, and that should give us a final answer of 0.3125. Okay, this is very important, and I deliberately did it wrong so that you could see this, because this individual is one generation later than this formula accounts for. Alright, so you must keep that in mind when you do your calculations in the exam. So there's one final arrow diagram for that was part of this tutorial, and that is question 3. It gives us the diagram. I'm hoping that most of you have your tutorials with you. I'm not going to redraw the diagram. Sorry, I hope this is staying in focus. So I'm just going to draw the condensed version of this diagram. So remembering that we start from the bottom. So we start with x. X has parents D and S. Okay. D has parents S and 3, which is a bit arbitrary. Okay. S has parents 2 and 1. Okay. 1 has parents 4 and 5. And 2 also has parents 4 and 5. Okay, so 1 and 2 are siblings. The siblings which also mated to have an inbred child, which is a little unfortunate, but good for practice for us. So the first thing we do is get rid of unnecessary individuals. In this case, it is just 3, because these individuals at the top here have 2 arrows going away from them, even though there's nothing coming into them. Also, that's proof that individuals 1 and 2 are full siblings, not just half siblings. Excuse me. Alright, so what we should see now, so let it focus. Now it asks us to calculate the inbreeding coefficient of S. Now most of you should be able to tell now, we've already identified that here's one inbreeding event here, and here's another inbreeding event here. Don't be worried about the fact these arrows have crossed, because they are parents. You could draw this inbreeding event circle using 5 as your top value. Sorry, I can't keep my board stable. You could use 5 as your top value or 4 as your top value. It won't make a difference to the calculation. So in order to calculate our inbreeding coefficient of S, we do the exact same thing that we did before. So for S, it would be the number of individuals excluding S, which is 3, and that'll give us 0.125. Nothing fancy about that. And I think that's all that question 3 asks us, but it could potentially ask us ask us for the F value of X. In this situation, we have 3 individuals, 2 if you're not including X, so 2 times 1 plus our FS value, and we calculate. Now, just to prove what I was saying earlier, in this situation, S is at the top of this inbreeding event, so we don't need to minus another 1 from our N value, so we can just calculate it straight. So it would be 0.25 times 1.125, and that should give us our value at the end. Yeah, so that value you can calculate with your calculator. So the steps that I promised I would write down, they go like this. For your arrow diagram, you want to start with your youngest individual and then draw up to the parents. Then you're going to eliminate individuals that either, so if this is individual A, don't have any incoming arrows, or only have 1 outgoing arrow. And you're going to repeat that until you have closed circles. Then using your closed, then you need to draw your closed, let's just do this, closed circles, and those will be your inbreeding events, and that's how you can work out your F values from your calculations. Okay, thanks guys.